Alright, hi everyone. We are now solving the second example of chapter 2. It is question 18. Let's read the question first. Question 18. Find the magnitude and direction of the total electric field due to 2-point charges, Q1 and Q2, at the origin of the coordinate system as shown in the figure. So what we see on the figure is a coordinate system in the X and Y dimension. There is two charge on the coordinate system. So we have Q1, which is 5 nanocoulomb, and is located on the negative y-axis 0.02 meter from the origin. The charge Q2 is equal to 10 nanocoulomb and is located on the positive x-axis at a distance of 0.04 meter from the origin. Now, just like in the first chapter, the first thing we should do is draw a force diagram. Actually, it's more like a vector diagram. And again, this will minimize the chance that we make a mistake with the plus or minus sign for the 1D vector. So here, we first look, both charges are positive, which means that the electric field line will be emitting outward from the charge, which means that this charge over here is emitting an electric field line outward in all direction. So from the point of view of P, the electric field line from the second charge is pointing toward the negative x-axis. So E2, so the electric field created by the second charge, is pointing in the negative x direction. E1, following this similar logic, this first charge is emitting electric field line in all direction outward. So from the point of view of the origin, the electric field line coming from Q1 are pointing upward. So E1 is pointing upward. Now notice, this simplifier will work a lot. These two vectors are already in 1D, all right? So that means E1, the vector E1 is equal to plus, although we don't write the plus there, it is still there, E1y. So it is equal to the component in the y direction. And this is a quick simplification that we can do because we know that there's no x component. Same logic with E2. The vector E2 is equal to minus E2x. Now, just a reminder that the plus or minus in front of this term indicate the direction. And this term over here, x, and this one, y, indicate that it is on which axis is this vector. In this case, this is a vector on the x-axis, and it's pointing in the negative x direction. All right? Now, at this point, what we need to do is simply calculate the magnitude of the electric field for both electric field, E1 and E2. So E1 is equal to Coulomb constant multiplied by the first charge divided by the distance between the point we are considering and the first charge. In this case, it is 0.02 meter, so 0.02 square, and we get an electric field of 112,500 Newton meter. For the second electric field, we use the same logic. The distance is instead 0.04 meter square. The magnitude is 56,250 Newton per meter. All right. Now at this point, we got our individual part. We simply need to add them together and recreate our final vector. So I'm going to erase at least the first diagram over here. So if you need to pause the video, do it now. Now really what I want to do is I want to draw the resultant vector, and I just realized that basically I could use that diagram. I'm still gonna redraw it. But we have E1, which is our E1y, so that will be our resultant vector EY, and the x component is pointing in the negative x. So this will be our E net, this vector over here. All right. Now, Now in this case, because the vector E1 was pointing strictly in the y direction and the vector E2 was pointing strictly in the x direction, we don't need to add the individual component. Basically, the vector E1 become our vector EY over here. So EY is equal to plus 112,500 Newton meter. EX then become minus, because it's pointing in a negative direction, 56,250 Newton per meter. All right, so we want to find the magnitude of that vector. What we do is we use the Pythagorean theorem. So E is equal to square root of these two values. So let's just write it completely. Let's compute this value. And it is equal to 126,000 Newton meter. Now, no, this is an approximated value. The true value is maybe 0.1% off. Now we need to find the angle. Let's find this angle actually over here. Now, if I want to find this angle and I am given the x and y component, I need to use the tangent. So tangent is opposite side divided by adjacent. So that means the angle has to be equal to the inverse function of tan of ex divided by ey. Now note again, I'm always using the absolute value, because if you get a negative here, it's not exactly clear in which direction it is pointing. Use absolute value over here, and then looking at the diagram, decide from with respect to which axis this angle is. All right. So if we compute these two values, we got we get an angle of 26.56 degree to the left of the positive y-axis. Now, by the way, if in a test you write your answer that way, so E, which is the magnitude, is equal to 126,000 Newton meter, and your angle, you find the angle to be 26.56, and you mention to the left of the positive y-axis. For me, that's fine. That's the answer I was looking for. If you want, you can also put the angle with respect to the positive x-axis. So basically, you add a 90 to this, you will get 116.56 degree. That still work. It is your choice, but you have to make it clear with respect to which axis you have taken this angle. All right, because it make a big difference. By writing it that way, there's no confusion. I know that you're talking about this angle over here, so I can recreate perfectly the vector. All right, so we are done for question 18. Let's move on to some more example.